Okay, so today we are going to start chapter 14. This is a chapter on periodic motion. Right? This is anything that is oscillating back and forth. Right? So this could be anything as simple as just putting a ball in the bottom of a bowl, and that ball is going to just oscillate back and forth. It could be a pendulum, right? Just swinging back and forth. It could be a glider on a spring, and the glider is just going to oscillate back and forth. It could be a hanging ball on a spring that's going to oscillate up and down. Or it could be something like a tuning fork where you bang it on the table and it oscillates and makes a sound. Or it could be something you don't want to oscillate, like a bridge, right? So that as an engineer, that may be your job to stop something from oscillating, right? But oscillation is really common in all fields. In chemistry, molecules are oscillating back and forth, etc. So to model an oscillator, our most simple model is just going to be a box on a massless table attached to a spring. Okay. When the spring is not stretched or compressed, it's going to be at what we call the equilibrium position, or x equals 0. Right? But if I stretch out this spring, we know that there's going to be a force trying to pull this box back towards that equilibrium position. And so that force is going to cause this box to accelerate in this direction. But once it gets to x equals 0, it's going to have a bunch of velocity. So it's going to pass x equals 0. It's going to compress the spring somewhat. And now the force is going to be in the opposite direction. And this is going to cause the box to swing back this way. Right? So this is our basic model of an oscillation. Sorry, let me get this animation going. Where I can see that this box is just going to oscillate back and forth on this table. It's going to pass through at the equilibrium position. And it's going to make it out to its maximum displacement and its minimum displacement. We're going to call it the maximum displacement the amplitude. Okay, so this is our basic model. We can see that the position as a function of time is oscillating back and forth. The velocity in green is also oscillating back and forth. And the acceleration in red is also oscillating back and forth. All right, so we're going to have to describe all the motion of this box in terms of some type of oscillating function. Okay, so to describe oscillation a little bit more, we have to first talk about what is necessary for something to oscillate. And the thing that makes something oscillate is something called a restoring force. This is any force that when you displace something from its equilibrium point, that force tends to restore it back to its equilibrium point. Right, so a spring has this equilibrium point, right, x equals 0, where this y-axis is located. And if I stretch the spring, I have a force in the minus x direction trying to pull that glider back to equilibrium. If I were to compress the spring instead, right, I have negative displacement. Now I have a positive force. Right? So when I have positive displacement, I have negative force. When I have negative displacement, I have positive force. So whenever that happens, there is this force always pushing me back towards x equals 0. That is what you need for oscillation, a restoring force. Okay. So if we again go through the full oscillation, I have a spring, it has an equilibrium point, I attach a glider to it, I pull the glider in the plus x direction, I now have a force in the minus x direction, so when I let it go, it's going to accelerate in the minus x direction. It's going to accelerate. When it gets to equilibrium, it's going to still have velocity. It's going to be moving to the left when it gets to the equilibrium point. At that exact moment, that string is not stretched or compressed, so there is no net force acting on that. It is not accelerating in that moment, but it still does have velocity, so it's going to overshoot. It's going to pass to the left, and once it moves to the negative displacement, we're going to now compress the spring. Once you're compressing the spring, we now have negative displacement but a positive force. So this time we have acceleration in the plus x direction. So that's going to cause this spring, this glider to slow down, stop, turn around, and accelerate again back towards the equilibrium position. Okay, so the net effect is that this object is going to accelerate back in force and oscillate. Okay. We can quickly look at a few different types of oscillators using some simulations. So I'll go back to the PhET simulations. First, let's do a hanging mass on a spring, excuse me. It has this equilibrium position, right? If I was to stretch out this a little bit and let it go, I'll see what happens. That spring is going to oscillate back and forth about that equilibrium position. And you can see the yellow arrow is the acceleration. Right, so when I have, let's say, negative displacement, right now it has positive acceleration. When I have positive displacement, when I'm above the line, you can see I have negative acceleration. And right when it passes through that equilibrium position, you can see the yellow arrow goes away. Right? At that moment, there is zero acceleration because you're at the equilibrium point. All right, so that's one type of oscillation. Another type of oscillation could be something like a pendulum. Right? If I have a pendulum and I let it go, it's going to swing back and forth. And you can see now the yellow arrow is the acceleration. This is both the acceleration due to gravity plus the fact that you have a tension force causing this object to go in a circle, in a circular path. And the net effect is this acceleration vector, which you can see is always restoring us back towards that equilibrium position. There's always a net force causing you to move back to the equilibrium position. There's other types of oscillation, of course. Something as simple as a half pipe or a skateboarder. Right? This person is going to oscillate back and forth too. This time the restoring force is the force of gravity. Right? This is a ramp problem pretty much. When I'm up here, we have a component of the force of gravity pushing you down the ramp. When you're at the bottom of the ramp, there's no net force on you. Right? You're not going to accelerate if you're at the bottom of the ramp. But if you're moving fast, you're going to overshoot. And when you're over here, we have a force of gravity down the ramp in this direction. So the net effect is this restoring force back to the equilibrium position. Okay, so that's another type of oscillation. And you can see that force is going to be one way to describe this oscillation. But you can also imagine that energy is going to be a way to describe these oscillations. This skateboarder is just oscillating back and forth between having potential energy and kinetic, right? At the top of at the highest point, they have a lot of gravitational potential energy. At their lowest point, they have no gravitational potential energy, but they have a lot of kinetic energy. They're moving fast. And so there's all sorts of oscillations. Some of them are more complicated, right? This is also another type of oscillation, right? It's more complicated to describe, but it is an oscillation, okay? So, okay, if we're going to describe oscillations, we need to introduce some language. So let's first introduce the concept of amplitude. So this is the maximum magnitude of displacement from equilibrium. All right, so this is something we're measuring in meters. We're going to use the symbol capital A for it. And it's basically your maximum position. Right? So if you're oscillating back and forth between plus 3 meters and minus 3 meters, your amplitude is 3 meters. The next word we're going to define is a cycle. One cycle is one complete round-trip oscillation. So if I stretch that spring out to its maximum amplitude, it's then going to pass through the origin, the equilibrium point. It's going to go to the negative amplitude, right? It's going to go to its minimum position. It's going to oscillate back through the equilibrium point, and then it's going to go back to where it started at the maximum displacement point. So that is one cycle. The next word we're going to define is the period. The period is the time it takes to complete one cycle. So this is always positive. We're just measuring a time. So it's some number in seconds. We're going to use a capital T for this. Instead of lowercase t, which is time, period is uppercase T, which is one specific time. This is the amount of time it takes to complete one complete round-trip oscillation. Okay, and then frequency is the number of cycles in a given unit of time. So this is also positive. Right, so if something is oscillating back and forth twice per second, the frequency is 2. Right, it's going back and forth 2 cycles per second. So we do have a specific name for the unit of frequency. The unit of frequency is the hertz, or 1 H, capital H, lowercase c. That's a symbol for hertz. You could also say 1 cycle per second, or 1 cycle per second mathematically, or you could just say 1 per second. All right, so that's totally equivalent, nice way to write frequency. All right, so since period is the time it takes to complete one cycle, and frequency is the number of cycles in a given unit of time, it turns out period and frequency are very related. Frequency is just 1 over the period, and period is just 1 over the frequency. So this is one of the most important equations we'll need. Okay, and as just a quick example, here's just an example of a quick oscillation where I'm starting at x equals 0 meters at time equals 0, and I start measuring at this moment. 3 seconds later, I note that the oscillator is now at some positive position, x equals 1 meter. 3 seconds later, at time equals 6 seconds, this object is now at 2 meters. 3 seconds later, now at time equals 9 seconds, the oscillator is back to x equals 1 meter. At time equals 12 seconds, we're back to the equilibrium point. At time equals 18 seconds, we're at minus 1 meters, etc. Right? And so 27 seconds later, we get back to our original starting location. Okay, we've gone through one complete cycle. Okay, so if we look more closely at this, we can figure out the amplitude, the frequency, and the period. The amplitude is just our maximum displacement. So it's a positive number. The furthest away we get from the equilibrium point is 2 meters. Okay, so that's our amplitude. Our period is just the time it takes to complete one complete cycle. So one complete cycle is not the amount of time it takes to come back to our original starting point, right? Because that would be this amount of time, 12 seconds. But that's not what's happening here, right? This object is going out, passing to its original position, but now moving the other direction, going to its negative amplitude location, and then coming back to its original starting position and moving in the same direction it started with. To start with, it was moving to the right. To finish with, it's also moving to the right. So one complete cycle has to include going to its max amplitude and its min amplitude and back to equilibrium. Okay. So the total period is 27 seconds. The frequency is just 1 over the period. This is a really slow oscillation. It takes 27 seconds to do one complete cycle. So the frequency is a very small number. It's a fraction of an oscillation per second. And it turns out 1 over 27 is 0.037 per second, or 0.037 hertz. Okay, and just the same basic idea, but we can look a little bit more closely at this. As this glider attached to the spring is oscillating back and forth, again, it starts at x equals a, its max amplitude. We always call x equals 0 the equilibrium position, and the minimum position it's going to reach is x equals minus a, right? Capital A is some positive number, it's a magnitude, so to denote its minimum position, that's x equals minus a. Okay, and if, again, we stretch the spring out, there's a lot of force when you stretch it out trying to restore it back to equilibrium. So at its maximum displacement, there's a large negative acceleration back towards the equilibrium point. At the initial velocity is 0. Since it has this large negative acceleration, sometime later it is now moving. It has some velocity in the negative direction. It still also has acceleration in the negative direction because it still has positive displacement. That means it must have negative acceleration. All right, still trying to restore it back to that equilibrium point. But you'll note the acceleration is not as big, right? Because the string is not as stretched as it was before. Right? And we know that the force of a spring increases linearly the further you displace it. Once this gets to its equilibrium point, it has acceleration of 0 at that moment because, again, there's no force from the spring, but it's moving really fast. That's the fastest it's going to be going, right? Because it's sped up all the way from here to here to here. The fastest it's going to be going is when it reaches equilibrium. So it passes the equilibrium point, starts compressing that spring. Once it does, it still has velocity to the left, but the acceleration has switched directions, right? Because the force is to the right, the acceleration must now be to the right, trying to restore us back to equilibrium. So I now have negative velocity and positive acceleration. That means I'm slowing down, right? The glider slows down, reaches its maximum negative position, negative times the amplitude, negative 1 times the amplitude, I should say. And this is, again, where I reach my maximum acceleration because I've now compressed the spring as much as it's going to compress, right? So that's why I have the biggest force. That's why I have the biggest acceleration. I'm going to have positive acceleration. At this location, I have positive acceleration and positive velocity, so I'm moving to the right and accelerating to the right. I'm speeding up. I again pass through equilibrium, again moving the fastest I'm going to go. I then again pass past equilibrium because I'm moving so fast. Now I have positive velocity and negative acceleration. I'm going to slow down, come to a stop, and switch directions. So that's our complete picture of an oscillation.